All right, and I'm going to share with you a screen that goes along with the Chapter 9. Okay. Okay, I think you probably remember this slide. It's relatively silly, and it has a population that goes along with 6 people, okay? It's hard to imagine a population of 6 people, but let's put it together anyway. What we're trying to do is we're trying to use these 6 students in a sort of a cartoon maybe, or an experiment that goes along with the proportion of females in this population. And we went through it pretty easily. These are all the 6 students are all the people in this population. I know that's silly, but let's keep that a fact. So the parameter of interest then, if we're interested in the proportion of females, is the parameter is P, okay? That is the parameter, and so if we were to look at the proportion of females, it would be 2 out of 6 or 1 out of 3 as a proportion. And so what this exercise is meant to do is sort of try to get all the different samples that we can get from a population of 6 people and a sample size of 2, okay? And so I know that we went through this last time we met, but I want to re-emphasize it. Okay. Okay, so there's 15 different combinations of 2 people, 2 students in each group. Okay, so we have every possible group with a sample size of 2. And what we're hoping to do is we're hoping to find the mean and the standard deviation of these sample proportions. Okay, a week ago we were talking about sample means. Okay, today we're talking about sample proportions. And what I'm emphasizing here is that a sample mean is X bar, and a sample proportion is going to be P hat. So the mean and the standard deviation of the sample proportions. So we're taking the mean of all 15 of these values, right? They are all proportions. All right, so if we were to start to think about what the mean and the standard deviation of the sample proportions, that's going to be 1/3, 2. Okay, so this here is mu sub P hat. So we're taking all 15 of the proportions, and that is the same as the original proportion. The sigma, the standard deviation of all these values right here is going to be 0.298. Now, how about if I were to take this silly example, and if I were to increase the sample size from 2 to 3, what is the variation going to do? What is the standard deviation going to be? Lower or higher? Go ahead.
If you increase the size, wouldn't the variation decrease?
Every day, okay? That's exactly right. We don't necessarily need the value, but we will say that it's lesser than 0.298. Okay, so this here is the mean, the same mean as the original parameter. So we want to build the same sorts of properties that go along with this. Okay, so rule number 1 is mu sub p hat is equal to the population proportion. Okay, so here is the statistic right here, p hat, and this is the parameter p for the population proportion. And then we also have a rule that goes along with the standard deviation sub p hat. And just to be sure that you understand what this term right here is, this is P, that's this P right here, okay? That's the population proportion. And if we know the population proportion, then we know what the opposing, so if we said that P is a proportion of 0.7, what would be 1 minus P? If we had a proportion of P is equal to 0.7, what would 1 out of a 1?
0.93.
Say again?
Is it 0.93?
Yes, it is, okay? So once we know what P is, then we can understand what this term is here. And of course, we're going to take this and the square root, and this is over the sample size, okay? So we have this rule right down here. So we have to think about the idea of a sample size. What is an appropriate sample size? Okay, so let's think about that. So I think that's where we left off, and I'll start with this. Okay, so we have this fall semester, 2008. We have 18,516 students enrolled in California Polytechnic State University. Of these students, 8,091 are females, and that proportion then is a 43.7%, or 0.437. Okay, so we're going to think about this. Cal Poly is the population, and this is the proportion of the student body that are female. Okay, so we're going to take the same sort of approach that we used a week ago, maybe, and generate 500 samples. Okay, 500 samples for each of the following sample sizes: 10, 25, 50, and 100. And we're going to compute the proportion of females for each sample. Okay, 500 of samples. Okay. So the next page will show the histograms that go along with the 4 different sample sizes that we are thinking about. Okay, so let's first think about what these are. So here is sample size of 10, 25, 50, and 100. Okay, and on the x-axis, what do we have as the scale? Okay, we have p hat for each one of these. The scale goes from 0 up to 1. All right, and it can't be any larger than that. All right, so a sample size of 10 brings us with this sort of histogram. It looks very symmetrical. It's bell-shaped, and it has a center sort of right around 0.43, I think it was, or 0.4344. Okay, so that's a sample size of 1. Sample size of 10, and we're going to look at 25, and we can see that again we have this center right over 0.43 or 0.4, and it is a symmetrical distribution, I would say, and it's more narrow in its variability than the histogram for sample size of 10. And that's the same case when we bring it down to a sample size of 50 and a sample size of 100. The variability that is going across the x-axis here is getting smaller, more narrow, as the sample size increases from 25 to 50 and to 100. Questions? Okay, yes, I think the proportions are centered, the histograms are centered on 0.43, 0.44. And as the standard deviation, as the sample size increases, the standard deviation of the distributions will decrease. Okay, and the shape is very symmetrical. Okay, so here's another example that we can use. All right, so there's a development of viral hepatitis after blood transfusions. Boy, that's a really serious thing. And so the article here reports that hepatitis occurred in 7% of the patients who received a transfusion during heart surgery. So let's try to simulate the sample sampling of the population with the blood recipients. Same sort of thing here. We're doing a 500 samples and 10, 25, 35, 45. I'm sorry, 10, 25, 50, and 100. Now, what we're doing here, this proportion right here would be 0.07, okay? This is on the low end of the scale that goes along with the scale along the x-axis. So if I were to use this, this histogram, 0.07 is right on this edge of the histogram, okay? The other one, the center, was along this line right here. So we're now using, we looked at this, but now we're using something that is very small to think about proportions. Okay, so let's think, we'll have a few histograms here, 500 samples and different sample sizes. Okay, so this here is a different picture than we saw with the other 4 distributions, okay? So with a sample size, with a proportion, the 0.7 is right down in through here. And this is sort of not symmetrical, okay? Here is where the mean is, but it's not symmetrical. That's a sample size of 10. If we were to use a sample size of 25, we still see sort of skewness here, but not the skewness that we see in this first histogram. All right, so the variation across the x-axis is very large here and much narrower here. And if we come down to 50 and a sample size of 50 and a sample size of 100, we can see that at 50, we still have some sense of a skewness, but it is very much more symmetrical than the ones that are on the top. And by 100, if we have a sample size of 100, we again start to think about the scale here. It's very, very narrow. It goes from 0.02 to 0.6. And inside that, that interval, we can see that 0.7 is at the center with a sample size of 100. And it's very symmetrical. So what am I saying about this? So when we are dealing with either very, very small proportions or very, very large proportions in this situation, then we're going to get a skewed distribution when the sample sizes are large, when the sample sizes are small. And we may need to look at the sample size to appreciate this being a normal distribution. At what stage does this turn into a normal distribution? That's the intent here. Okay. So each one of the histograms are centered right around 0.07. It's called, it's hard to call, there's a center here, but each one is got a center at 0.07. And each shape starts to come about, the normal distribution, the shape of the normal distribution comes about as the sample size increases. Okay, so rule number 3 with proportions. When the n is large, okay, and p is not too near 0 or 1, the sampling distribution of p hat is approximately normal, okay? And that was the case when we were thinking about the females at Cal Poly, okay? We had a proportion that was 0.437, and that was not so near 0 or not so near 1. It was more in the middle of that. In that case, the sampling distribution can be considered approximately normal. Okay, so the farther away from 0.5, the larger the sample size must be for that sampling distribution to be approximately normal. And we saw that in the blood transfusion example. Okay, 0.07 is very far away from 0.5. And therefore, we needed a larger sample at, and what we saw was at 100, the sample size at 100 was probably good enough for our sampling distribution to be approximately normal. Okay, so here is the conservative rule of thumb. All right, so let's think about this for a second. So we want the sample size and the proportion to be the product of that to be greater than or equal to 10. And we want also, in the same way, we want the sample size times 1 minus the proportion. And that's got to be greater than 10. Okay? So let's take some numbers here. Let's take a look at 0.437. Okay, 437. What is the sample size that we need to get 0.37 greater than or equal to 10? Okay, I have my calculator out here, and I'm going to give you an idea. 0.437 times 20, okay, is 8.74. So if we wanted a sample size with 0.437 as the proportion, we probably need something up around 30. 0.437 times 30 is 13.11, okay? So in this particular case, when the value is very close to 0.5, n has to be somewhere near 25, a sample size of 25. Okay, everybody sort of see that? Questions? Okay, So let's do another exercise. What would you say 0.7? I'm sorry, 0.07. What would be the sample size for that proportion to get this assumption going? What would be that? Well, an easy way to think about it is 0.07 times 100 is going to be what?
7.
It's going to be 7, right? So Eric, is that greater than or equal to 10?
It is not.
It is not. So we need a sample size, not at not at 100, but maybe at 150. 0.07. Excuse me. 0.07 times 150 gets us to 0.07 times 150 gets us to 10.5. Okay, so this assumption, when P is 0.07, requires the sample size to be close to 150. And that's what we're thinking about in this particular case. Okay, so that's the assumptions that go along with proportions. Questions about that? Okay, so only 6 out of 200 patients contracted the hepatitis. Does this result indicate that the true proportion of patients who contracted hepatitis went when a screening was less than 6%? All right. So here is what I'm suggesting to you. The assumptions that we have to make to give us a sampling distribution that's approximately normal. We have to have a sample size of 200 for a proportion of 0.07. That turns into 14 is greater than 10. And the alternative, the opposing 1 minus P, has the same sample size. And of course, 186 is clearly larger than 10. So what is the mean and the standard deviation of the sampling distribution? The mu of the P hat, sub hat, is going to be 0.07, and that was the original proportion, and 0.018 is the standard deviation of that same proportion. All right, so what can we do with this particular situation? We can start to think about 0.07 as the center and a standard deviation of 0.018. All right. So we would have a P.03. Okay. Okay, lesser than this, if we had a 6/200 here, this is the proportion. 6 is the proportion, the number of people that showed a hepatitis over 200, and this is the proportion. So we're comparing this against the population proportion. And the z-score here would be -2.22. Very, very far away from the mean on the left side of the distribution. Okay, so this would be 0.0132. All right. So this small probability tells us that it was unlikely that the sample proportion of 0.03 or smaller would be observed through a screening procedure. And it was seen to be ineffective in terms of that outcome, okay? All right, questions? All right. So the new screening procedures appear to yield a smaller incidence rate of hepatitis. Okay, so that ends chapter 9. Okay, so I'm going to use about 10 minutes to introduce another chapter. Okay, let me get another chapter here, please. And hold up. One second, please. So, I've lost it. Okay. All right. Okay, there we go. Sorry about that. Okay, so what we're going to do for the rest of the semester is we're going to start to think about confidence intervals, okay? And confidence intervals are a way of inferring something about an estimate, okay? And when I say an estimate, I'm using maybe X bar. Another estimate might be P hat. And in those estimates, we've seen that if we get more than one mean, and we get a second mean or a third mean, those sample means are very variable, are extremely variable. And so what we need with those estimates is we need an interval for which we are confident is incorporating the population parameter. So that's what a confidence interval is. It's sort of a point estimate at the center, and it has an interval that goes along with the amount of variance around that estimate. Okay. So let's take a look at this here. Okay, Chapter 9 in your book, confidence intervals. All right, so let's take an easy idea. We have a bag of M&Ms, and we want to know what is the proportion of blue candies. All right, and so there's a big bowl of M&Ms, and we see a couple of blue candies, and we ask the question, what would be an estimate of the proportion that are blue? So here is our sample. All right, we would have a sample proportion and a statistic. Okay, so we want a single value, one value, a point value that gives us an estimate of the proportion of blue candies in this sample. So this is a definition. This is an idea that goes along with confidence intervals. First, you need a point estimate, and that's a single number, and that's a statistic. It could be p hat, it could be x bar, but it is a statistic that gives us a value from the data set, a data set that might estimate a population characteristic. So say the population characteristic is right here at the arrow, okay, the small arrow that you see on this, and that the point estimate is close to the arrow, but it's not exactly on the arrow, okay? So the point refers to a single value, all right? And we have the single value, it's very close to the population characteristic, but it's not exactly on it. So now we want to take several different samples, okay? And of course, they are going to be spread across the scale from being very far away on the left side to being very far away on the right side, okay? And so this is the sampling variation that goes along with this population, okay? So we have several different point estimates that could be showing us some information about the population parameter. Okay, so let's think about this situation here. So we're thinking about 7,421 students at 40 colleges, all right? And we want to know how much they're using the internet, okay? All right, so the authors start to think about this a little bit, okay? And they want a proportion of the college students that spend more than 3 hours a day on the internet. Boy, I'm definitely doing more than 3 hours a day these days. So anyway, here is almost 3,000 out of 7,421 that reported using the internet more than 3 hours a day. So that proportion is 0.404. Okay, so that is a point estimate for the proportion of college students being on the internet more than 4 hours a day. That's an example of a point estimate. Now, where that is on being close or far away from the population proportion, we don't know. Okay, so I think I'm going to stop here because this is going to be a longer explanation. And I think I'll let you go for the day and pick up here on Friday. Okay, so we're going to be looking at confidence intervals, and you might want to start looking at Chapter 9 and building some background for Friday's lecture. Okay, so I'm going to bid you a good day. It's great to be in front of you, and have a great day.
Thank you.
Thank you.
Thank
too.
you.
Thank you.
Thank
Have
you.
a good day.
You too.